Hello, dear students. So this is our 13th lecture on tensors, and in the previous lecture we have discussed about what's basically tensor, what is basically contravariant and covariant to this tensor. And you know that when we have this index on the superscript, so that's basically called contravariant, and if you have this index in the subscript, that's called a covariant, right? But so to visualize how this contravariant and covariant, how you can distinguish them, so I basically in my so you just watch my that previous video, so where it is very clear that how you can distinguish between that contravariant and covariant, right? So in addition to that, so we can write that. So this is basically our that contravariant, because we have this index in the upper the superscript, that's basically called contravariant, and you can write it in terms of this. This is the length element, you are dividing it by length element, and this that this regular vector you are defining, right? And similarly, you can define this covariant because the index in the it is in the subscript. That's this level covariant. You can define it by multiplying by the length element, right? Okay. Now, in addition to that, we can have this. We know that this Minkowski matrix G mu. I can rewrite this term as. So this I can write as that G mu. So if you remember that, that can be written as. Okay. So this is basically because the h mu square you are multiplying the square of the length will be, because when mu equal to mu, so this will be equal to, this will be simply that this should be equal to 1, and this is simply the square of the length. Because why I'm doing this thing, because we need to write when we're writing this contravariant and covariant, because they should remain invariant and they should have the dimension of length, right? So that's why I'm multiplying by this here, I'm dividing here, I'm by multiplying by that length element, right? And this G mu nu, if you remember that, this G mu nu, so this is our that. Okay. So that means if you write this as, so that means if you compare this with this, so our this h mu you can write that. So that is you can write that HR. What's our HR? HR will be equal to 1. Okay. So that means how we can define that. So HR will be this one, H theta will be this one, and H phi will be this one. Now, in addition to that, if you want to take its variation now, because you know that but this is the importance of that. If you transform or if you multiply this gradient to some vector or some scalar function, if you act some gradient on some scalar function, it forms a vector, right? So that means if you take its variation with respect to some gradient, with respect to some partial mean, right? Okay, so that means we can write them. So we can write this as. Uh, I can write now that partial mu as. So that will be written as that's equal to h mu, right? Okay. Or you can write this as delta mu will be equal to that's equal to 1 by h mu. So that means how you can relate how this gradient varies, how it gets transformed, right? So that means our this so delta r from here, so our delta r will be equal to, so that will be equal to, if you remember this, so this is our 1 by r, or you can add that this is our partial r, so that is partial r, or you can add this partial r, and this that's equal to 1 by theta, 1 by r square, partial by partial, and this develop phi. Okay. Okay, so that means you can write then what's our nabla square from here, right? So nabla square will be simply that take sum of this, so that basically gives us that nabla square, right? And with some proper these basis vectors, right? When writing that nabla equal nabla square some er square, So you need to multiply with some proper basis, and that basically gives us that Deborah square, right? So this was what we have discussed so far. So this was all about this contravariant and covariant these tensors. Now next topic is if you talk about the tensor algebra. Suppose we have some tensors of different ranks, right? So how we can contract between we can make contraction between the tensors, or we can multiply that tensor by some scalar. So there are some properties of this that's basically called the tensor algebra, right? So suppose we have some vector, some tensor of contravariant tensor. Uh, so we have some contravariant plus covariant, right? So that means if we have some A alpha plus some B beta here, right? So if we sum up these indices, that's alpha plus beta, that basically gives us the rank of the tensor, right? So that means our that alpha plus beta, that's a rank of. And in addition to that, we have one more property. If we multiply some tensor by some scalar, if we have some tensor like we have T of some alpha gamma, and I am multiplying it by some scalar, some uh, C here, right? So I'm multiplying this tensor by some scalar, right? So it gives us the tensor of same rank, because this is a tensor of rank 2, because it has that this alpha in the contravariant in the superscript and this gamma in the subscript, right? And you're writing that it's this rank will be that alpha plus gamma, right? So it's a tensor of rank 2. Now what I'm saying that if we multiply this tensor by some scalar like 1, 2, 3 number, right? So that means the rank of tensor remains same, right? So that means we can have some new tensor, because it is some t, it can be some u alpha. So rank remains same. So इसकी rank same रहेगी. You can get some new tensor but have same rank, because the rank of this tensor is 2, so you can have the same rank when we multiply it by some scalar, right? And one more property is that if we talk about now, if we have one more tensor of rank 2 alpha beta, so we can rewrite this as, so this is basically if we have some tensor of rank 2, like this is the tensor of rank 2, so you can write this as a sum of two tensors having same rank, right? Because when you add them, so you can get same rank. So that means, so this is, you can say that this is a tensorial action, tensor action. So that means you can add these two tensors, but the rank remains same here, right? So you are adding these two tensors having same rank, and you are getting the same rank, right? So that means by adding the tensors, the rank remains same, right? And in multiplication, so that's also clear. Now one more property is that if you talk about now the contraction, right? So if we talk about now, if we have one more property, that is, if you talk about that, if we have this some t of alpha beta, so this can be written as some u and v, right? And this will be alpha gamma and gamma beta. Okay. So this is simply because it reduces the rank here, right? So because this is our left hand side is basically tensor of rank 2, and on the right hand side I'm saying now, so this is again a tensor of rank 2, because I'm doing contraction here. So this and this will contract, so this and this will contract, so we'll get the same rank, right? So this property is called as a tensor contraction. Because the product between these two tensors, because both these tensors of have two ranks, so we should expect that its rank should be 4 here, right? But there is contraction of this gamma with gamma, right? So I'm getting same, that the tensor of rank, and this is called the contraction. And similarly, if we have tensor or some tensor of some rank 4, like we have this alpha, beta, gamma, and delta. So this can be written as a product of two tensors of different ranks, right? And some V of, right? So this is, you can say that this is that tensor product. So this, so our left hand side thought that was basically a tensor of rank 4 because there are 4 indices contravalent. So this is tensor of rank 4. But if we see, if we have a look on the right hand side, so we have now the product of two tensors but of different rank. So one is having tensor of rank 2. So that means this is basically tensor outer product. You can say that this is tensor outer product. Right? तो हम यहाँ पे कर सकते हैं because you can take multiplication between these two tensors, right? And the rank will be then 4 because 2 plus 2, right? Okay, because so it is clear. So these are basically some tensor algebra, and in addition to that, if we there is one more property. अगर हम देखेंगे, if we do the contraction of same indices, suppose I have some tensor of some rank 2, I am basically making contraction with the with some tensor but having same rank, जो जिनकी rank same होगी. If you have some tensor जिनकी rank same होगी, if you do the contraction of that this tensor, so that basically gives you a scalar, right? So what I am writing now, that means if you talk about the contraction for all indices, तो मैं क्या लिखा हूँ, तो दैट मीन्स यहाँ पे हम कंट्रैक्शन करें बट फॉर ऑल इंडिसेस, राइट? सपोज we have some that R of alpha alpha, right? Okay, so this simply gives you a scalar. It gives you some scalar number, right? Or you have some S, some mu u of tensor of rank 2. So this again is scalar, right? So that means if we do the contraction of such tensors, right? So उसमें क्या हो जाएगा? So I will give you an example. Suppose if you want to transform now, if you have some this R prime, some mu, because this is the same tensor, this tensor of same this. You are basically making contraction of same rank because R mu here, right? So it is like some T11 or R11, R22, right? This is same rank, right? So this I can write as, so you can rewrite this as, so this will be some R of some rho sigma, right? So I'm basically transferring it from some this unprime to some prime system, right? So this I can write by some transmission coefficient, that's partial acus by partial acus. Okay, and in the superscript you should have minus mu prime, prime mu, and this will be equal to that. Okay, so this is what you can get from here. So this is the tensor of you are contracting the same tensors of same ranks with some transformation matrix and then this, right? Because if you relate this as, so this will be equal to this one. This one is equal to rho sigma, right? Or of, right? So this is the one. Because you can decide this will cancel, so this will be the delta rho of the sigma. So when the rho equal to sigma, so you should get that because if you put that rho equal to sigma, so this delta of rho sigma that should be equal to 1, right? Or this will be equal to delta of, or this is further equal to or of sigma, right? So this is not that. Okay. So that means this is pure scalar number, right? Like if you talk about now in special relativity. So if you remember that, so अगर आपको maybe we have not discussed that, like in special relativity, you are writing that dx prime, you are writing that dx mu, dx mu. So अगर आपको, so if you have studied this this special relativity, we are writing that 4 vector in this way, right? So this purely gives you a scalar because this is dx square. So ये हमें square of the length element देगा and that's purely scalar, right? So that means यहाँ पे contraction same element का हो रहा है because it's a tensor of rank 1, right? Mu, and you have the same this rank for the second element, for the second length element, right? So this mu and mu will contract, so this gives simply ds square, right? Because okay, so I will show you that because we have that ds square equal to this, right? Sorry. So we have so many times we have used this expression that ds square can be written this way, right? So that means जब mu के बराबर होगा, so that means this d mu will be equal to, it will be 1, right? So despite it can be some ds square or it can be negative. So but in general it will be some ds square, right? So that means this is our that this length element is our that dx mu dx mu is our that length element, and this length element is a scalar. Okay. Or instead of that, if we write this, for example, if you go in this spherical polar coordinates, so if you talk about that, we can use that in this expression because if you remember that this one, right? So if you write it here, okay. So if you write for, because we know that x equal to, okay, and that theta will be equal to, or you can add that r square will be equal to x square plus y square, right? And you can write here, we can put here, let our x will be equal to some rho and y equal to sigma and rho. Okay. So if you use this transformation, so that means we should get that partial r by partial x. Sorry, it should be y here. Right? It should be y here. Y partial x by partial r and plus partial theta by partial y and partial x by partial, right? So you just check from here because you put that x equal to rho, so x equal to rho, so you will get that partial r by partial y, and then partial y by partial r. Because when you put that y equal to rho, so use this transformation matrix, so you should get this one. So that means when rho equal to this sigma, so you should get the same length. That means dx by dy ka whole square. Sorry, dx by dy ka whole square. You will get when rho equal to sigma, right? So when rho equal to sigma, you should get that partial x by partial y, and that is simply our length element. So if you use for this Cartesian coordinates, if you write that in terms of that theta and phi, from rectangular to some theta, so we can write it this. So I'm basically giving you the example. So how you can write that if you contract this, you can if you contract this same these ranks, so you are getting. Now another that factor is that if you talk about now we need to see how if you transform this, if you integrating some function, so if you transform that integration, so that means if you write now if you go from some xy frame to some x prime y prime frame, right? तो यहाँ पे हमें देखना है कि if we go from one frame to another frame, how this integration varies. So that means how this integration is performed. Like we have some function f of xy, So this integration of this thing, that is dx dy. So how it goes, if you make transformation to some new coordinates like theta and phi, or sorry, so it should be r theta. Huh? Okay. Okay, so this is basically how this integration transforms, right? If you go from some this Cartesian to some this polar plane polar coordinate system or theta, right? तो वहाँ पे हमें देखना है कि how this integration changes. If you go from some this xy to some r theta coordinate system, right? So in that case, so that means our length element in that case will be equal to that is dx prime dy prime. So this is related with some new coordinates. This is dx dy. So you can relate it by some that's basically called a Jacobian, right? And the Jacobian is basically the ratio, or you can take the determinant of that these length elements, right? And this is how you can relate from some unprimed to some private system with the help of this Jacobian, right? So I will give you an example. If you talk about some Euclidean polar coordinates, there is some polar coordinates. So we can write that x equal to. Okay. So Jacobian for this will be equal to that will be equal to that partial x by partial r. Okay. So that's partial x by partial r, partial x by partial theta, partial y by partial r, and partial y by partial theta. This is how you can relate because uh, so you need to write this length element if you go from some unprimed to primed system by multiplying this Jacobian here, right? And this Jacobian is simply that it is the determinant of that differential elements, taking variation of this x with respect to that r and theta, and then y take its variation with respect to r and theta, right? So if I take the partial x by partial r from here, so partial x by partial r will be cos theta here, and partial x by partial theta will be equal to minus r sin theta. Okay, let me write it here. So first will be equal to cos theta. Okay. So when I take this is purely the determinant. So this will be that r cos square theta plus r sin square theta. So that means our Jacobian will be, or this will be equal to. So if you check, so just have a look on this. So यहाँ पे क्या आ जाएगा? So this will be simply that r cos theta into cos theta. So that's cos square theta, and then minus. So this will be plus here r square r sin square theta. So this will be equal to that r cos square theta. So that means our Jacobian will be simply that r. So that is, so that means if you write now, like if we have this x to go from x to theta, right? So you need to multiply that by r. So that r is simply your Jacobian, right? So like if we are writing that x equal to some r cos theta and y equal to that r sin theta. So this basically is our that this is our that Jacobian, right? And it basically so the Jacobian, as I already told you, so Jacobian is basically the determinant of these transmission coefficients, right? So because this is very clear here, so if you have a look, so this is these are basically the what that this transmission coefficients. So if you transform it from some unprimed to primary system, and this again the transmission coefficient for theta and for r and for theta, right? For x and y individually, तो separate लेते हैं. So that means जो हमारा Jacobian है, ये हमारा ये हमें relate करता है if you go from some this rectangular to some plane polar coordinates, right? So you need to multiply by some factor, and that factor is our Jacobian. And that Jacobian, as I already told you, So that is purely the determinant of those transmission coefficients, and those are transmission coefficients, right? And in addition to that, we can also write now if we relate now. So if I relate now, this G mu nu. So G mu nu. So how I can write this as in terms of that this if you transform this G prime, the Minkowski schematic. So how you can relate it by some if you have some nu that is rho c. Okay. So you can also write it in terms of the Jacobian, right? Because Jacobian is already that it is a determinant of those transmission coefficients. So that means I need to write those transmission coefficients here. And those transmission coefficients will be something like that. That partial x by partial x, partial x by partial x. And this will be prime mu, right? And this will be prime mu. And this will be rho and sigma. Okay. So this is the equation, right? And you can write this as if you write that mu equal to nu prime, like mu equal to nu prime, right? Okay. So or so you can write when mu equal to nu prime, so this is equal to 1, or you can write this as this G prime. If you take determinant on both sides. So this will be the determinant of this, and take that determinant for this thing. Okay. So this is our that. This G prime is our that. This is simply that G square here. Which implies that or J will be equal to that is square root of G prime. So that means we can also write the Jacobian in this form also. So that is the ratio between that square root of that this Minkowski matrix. Right? Take the determinant of that. उसका determinant हमें लेना because this is the modulus of that. We're taking the modulus of that Minkowski matrix, right? And that basically again gives you the this Jacobian, right? If you transform for this from some unprimed to some new frames, from some primate to some unprimed system, right? So you need to multiply the Jacobian, and this again you can write in terms of this square root of this, right? And so this Jacobian, why basically we use the Jacobian? So this is very important. So we have discussed the Jacobian, how we can write the Jacobian. Why I am writing the Jacobian? It basically prevents our this array element from being a scalar. So it basically prevents our array element from being a scalar. Otherwise, so it doesn't remain as a scalar at that point, right? So it basically helps us to prevent this array element from being a scalar. So that is the importance of using the Jacobian, and you can also see here. So from this expression, or you can rewrite this as, so this can be written as that square root of G prime, or this is dx prime, dy prime equal to dx dy. Right? So this is this line segment remains invalid, right? And as I already told you, this why we basically use the Jacobian, it basically helps us to make that to you can say that it prevents that area being a scalar, because so this is why we use the Jacobian, and we have discussed that. So in our coming lecture, we are going to discuss some new lectures. So thank you very much.